Hello everyone, good morning. My name is Che-Wei Chang. I'm a PhD student at CPES, and the topic I'm going to present today is a passive balancing method for dynamic current sharing of parallel silicon carbide MOSFET with Kelvin source connection. And this project is working with the US Department of Energy and the General Motor. This is the outline of today's presentation. First, I will give a brief introduction, and then I will introduce the mechanism of the dynamic current sharing. And based on the mechanism, the parasitic impact study can be studied, and we can also provide some layout suggestion, the practical layout suggestion. And later on, we proposed a current balancing method, which is completely passive method without any active control, and with the experimental with verifications, and finally, the conclusions are given. So for the background, typically, for the power level around several kilowatts or even lower power range, using the discrete devices shown on the left figure may be enough for the current capacity. However, when moving toward a higher power level, high current demand in applications such as, for example, the electric vehicle, more electric aircraft, train, or ships. So therefore, paralleling the devices is a popular and economic approach to augment the current capacity. For example, in the bottom Tesla Model 3 inverter, you can see they're paralleling the discrete devices for their three-phase traction inverter. Or in Wolfspeed's module, you can see they're paralleling dies for the higher current capacity. Or in some cases, for example, Infineon hybrid pack module, you can even parallel the modules, and they all belong to the same structure that you're paralleling the devices in your circuit. However, when paralleling the devices, it may cause the current sharing issue. So figure on the left shows the discrete devices in parallel, and the figure in the middle shows one of the example waveforms of the double pulse test current waveforms of 4 different drain currents. If we zoom in the turn-on transient, you can see the currents are very unbalanced during the dynamic switching transient, and it may lead to the issues of unequal losses, unbalanced junction temperature, and we know that the silicon carbide MOSFET threshold voltage has the negative temperature coefficient, which means that one of the devices may become like a thermal runaway, and eventually your devices may explode and decrease your system reliability. So in this case, a current balancing solution is needed or required for when we're paralleling the devices. And the current sharing issue usually happens in 2 main regions if we look at the switching waveforms. So figure on the left shows the lumped switching waveforms, and you can see the first region is the static region, whereas the MOSFET is conducting the constant current. The second region is the dynamic current, which means that the MOSFET just being turned on or turned off. And it can also be affected by 2 main factors, and I want to use the half-bridge example on the right to show what is the factors. So for example, your paralleling device is showing in the pink rectangular spaces, and the first factor may be caused by your device mismatch. You are difficult to ensure that you have identical devices. And another factor is your layout mismatch. For example, from your AC node to all your parallel devices, or from your parallel devices to the common DC minus node, and you're hard to ensure that all of the traces are equal. So these 2 factors may impact the current sharing issue. However, today's presentation, we want to focus on the dynamic current sharing caused by the layout mismatch, because during the static region, the MOSFET will have a positive temperature coefficient, which may result in the automatically balanced steady state currents. And the device mismatch issue can be alleviated due to the manufacturer's technology in the future. To study the mechanism, a model needed to be derived. So figure on the left shows the half-bridge example, and we want to highlight or focus only on 2 devices as shown on the right-hand side, and the total current I load will be divided into the 2 drain current, ID1 and ID2. And in this circuit, the parasitic component include the drain parasitic, for example, the LD, and also the source parasitic inductance, the gate parasitic inductance and the gate resistor, and also the Kelvin source parasitic inductance. So for this circuit, since the MOSFET are working in the saturation region during the switching transient, we can replace it by the voltage control current sources, which is controlled by the charged gate source voltage on your gate source capacitance, CGS. And the gate source capacitance will be charged by the gate current IG. And if we derive this equation by using the simple KVL loops plus the KCL relationship, and we have to make a very important assumption that devices are all identical in our derivation. Eventually, we can study the dynamic current sharing by using a very simple RLC equivalent circuit, where the voltage source in this circuit is only depends by your source mismatch. And also times the DIDT. The DIDT is from your I load, which should always be positive if we assume we're studying in a turn-on junction. And the current in this circuit is the differential component of two gate current, IG1 minus IG2. So the RLC in this circuit should be the equivalent R, equivalent L, and equivalent C. They all have a detailed equation, and you can always look in the detailed equations in our more detailed publication, but I don't want to show it in here. But the degree of your unbalanced gate current will be determined by the combination of this RLC. And based on this mechanism, or this circuit, we found out that the feedback mechanism exists during the dynamic current sharing. And you can see that I didn't highlight the drain inductance on the left-hand side. This is because the dynamic current sharing mechanism is totally independent of your drain inductance parasitic. So I want to show one of the example waveforms to explain the mechanism. For example, the waveform, experimental waveform on the right-hand side, where the source inductance 2 is higher than the source inductance 1. And first step is when both VGS reaches the threshold voltage. So the MOSFET started to conduct the current at this point. But because the LS2 is higher than LS1, which generates a positive voltage in the equivalent circuit, it will also generate a positive IG1 larger than the IG2. So you can see during this transition, the IG1 becomes larger than the IG2, and it will result in the different charging speeds, so result in the unbalanced gate source voltage, VGS1 larger than the VGS2, and then eventually it will lead to the unbalanced drain current, ID1 larger than the IG2 during the dynamic transition region. So for the dynamic current sharing, you can see that it is most sensitive to your power source layout mismatch. And also the degree of this unbalanced degree will determine by the combination of R, L, C equivalent, the equivalent R, equivalent L, and the equivalent C. And what are the practical layout suggestions can we provide learned by this circuit is that, for example, to enhance the current sharing, first of all, you can make the equivalent voltage equals to 0, which means indicated that you have a very balanced source layouts. And I want to show 4 different waveforms on the right-hand side. They are the drain mismatch only, source mismatch only, and the bottom 2 are the gate and Kelvin source mismatch only, respectively. But you can see that only happens when the source mismatch appears in the circuit. You will have a very unbalanced dynamic current sharing among the 2 parallel MOSFET. While the drain, gate, Kelvin source, the current are very balanced, even they have a mismatches around 16 nanohenry for each cases. So apparently, the dynamic current sharing are only unbalanced under the mismatch source, and while it's dependent to other different mismatches. And another method to enhance the current sharing is to make the loop impedance of this equivalent circuit equals to infinite. And how do we do that is the total impedance magnitude will be inversely proportional to your Kelvin source parasitic, but also positive proportional to the summation of the source parasitic impedance. Figure on the right, I want to show you the waveform example of the impact from the Kelvin source. So we studied the first one is the Kelvin source impact. And the top waveform is the gate mismatch gate current. The bottom one is the drain current of the 2 MOSFET. So this green line case shows when the Kelvin source in parasitic is equal to 10 nanohenry. If we decrease this 10 nanohenry down to 5 nanohenry, you can see the degree of the unbalanced current is slightly improved. Or we can even decrease it down to 0.1 nanohenry, which means you almost don't have any Kelvin source connection between 2 parallel MOSFETs. You can see the balanced current, the 2 drain current are almost balanced, even if you have a source mismatch in this circuit. So which means that the Kelvin source parasitic between parallel devices should be minimized. The second one is we want to study the impact from your summation of your parasitic source inductances, and I want to show you the experimental result to prove it. So this waveform shows the drain current waveform where The first case is the green one is when the summation of your source inductance equals to 12 nanohenry from 2 MOSFETs. If we increase it from 12 to 22 nanohenry, you can see it's slightly getting a little bit balanced. Or we can increase it up to 32 nanohenry, you can see two currents are much balanced than the previous case. So increasing the summation of your source parasitic inductance will help enhance the dynamic current sharing, but despite increasing the commutation loop inductance. And when we're talking about the commutation loop inductance, I want to show you another cases where you increase your drain inductances, because it also results in the higher commutation loop inductance. But if you look at the waveform showing on the right-hand side, it's also the experimental waveforms. You can see, although when we start at the 12 nanohenry of the summation drain source parasitic, if we increase it to 25 nanohenry or increase it to 35 nanohenry, the dynamic current sharing doesn't change at all. But this is because the entire mechanism is independent of your drain parasitic inductances. So this gives us the very two important note is that either you're matching the drain inductance or increasing the summation of your drain inductance has no benefit from the current sharing point of view. And also, if you really, really need to increase the commutation loop inductance, you are inevitably to avoid this kind of situation, you should increase your summation of your source parasitic inductance to enhance the dynamic current sharing. So we want to say, do we have the methods to improve our dynamic current sharing even if we have exhibit a source parasitic mismatch between two MOSFET? The answer is yes. So our solution is, we propose a solution. We propose to put the differential mode choke and add it into the gate driving path to balance two gate current, even if your power loop are mismatched. So when the gate current to IG are balanced, they will not see this differential mode choke on the gate driving path. But when the gate current IG are unbalanced, then this current difference, delta IG, will be suppressed by this large impedance of the magnetizing inductance Lm from your differential mode choke. And figure on the right just shows the samples of the DMC where the Lm equals to 25 and the 5 microhenry. So it's kind of like a small profile and like a small volume, even if we didn't really focusing on optimizing the solution, but we only need like tens of several microhenry should be enough to balance the current. So this solution will feature an easy and low cost, and it will automatically balance the drain current because you already balanced the gate current. And also it has no impact on your power loop commutation loop inductances. So let's compare the equivalent circuit between two cases. The left-hand side shows the original case equivalent circuit. The right-hand side shows the equivalent circuit of the proposed methods. And in those two equivalent circuits, the voltage source, REQ, LEQ, CEQ have all the same mathematical expression, but on the right-hand side, if we adopt our solution, additional terms appear in the equivalent circuit that can help to suppress the unbalanced gate current. And this value will be dominated by the differential mode choke magnetizing inductance Lm. So this Lm will appear in this turn and help suppress the the differential gate current, and eventually further leads to the balanced drain current. And let's look at some experimental verifications waveforms. Before that, I want to show the double pulse test setup in our lab. So the left-hand side shows the double pulse test circuit. The right-hand side just shows the setup. We're paralleling two MOSFETs, M1 and M2 from Wolfspeed Cree. They are the 1.2 kilovolt range of devices. And two currents, ID1 and ID2, can measure by two current probes inserted into the cutout of the board. And the source layout mismatch, we can see I implemented a small air core inductance on the right-hand side in this path to create the layout mismatch. And two MOSFET are both driven by the same gate driver IC, and also the differential mode choke are placed in the middle among two parallel devices. So I want to show the original waveforms where there's no mismatches. When there are no mismatches, this one shows double pulse test current waveforms, and we can zoom in the turn off junction and also zoom in the turn on junction. You can see that originally the two current sharing among two parallel devices should be balanced enough because they have an identical layout without any mismatches. But once, if we introduce the source mismatch into the circuit, the left-hand side shows the original circuit, the original waveform, and we can zoom in the turn-on junction. You can see the original current unbalance degree is around 8.3 amperes. When the DMC around 5 microhenry is inserted into the gate driving loop, the waveform is shown in the middle, and also the 25 microhenry case, the waveform is shown on the right-hand side. We can also zoom in the turn-on junction. You can see the unbalanced current is significantly decreased from original 8.3 amps down to 2.9 amps, and almost balanced when the DMC values is equal to 25 microhenry. So the current is much balanced after adopting our proposed passive solution. And another thing I want to highlight in this waveform is you can look at the current rising speed are almost identical in 3 cases. And we didn't change the gate resistor or tune any parasitic inductance in the circuit at all. So we only add the differential mode choke into the gate driving loop, and it all still result in the similar current rising speed. And also the proposed method can also be used for the multiple devices case, where in this case, the 3 inductances, LS3 is larger than LS2, larger than the LS1, and the original waveform is shown on the left-hand side, where after we adopt our solutions, the DMC of Lm equals 25 microhenry, the structure we're using, you can see all of the primary side are connected to the MOSFET gate, and another side is connected to the common gate voltage source. The secondary side winding are all in series, which means that it forces all of the gate current to be balanced among multiple devices. The waveform can show on the right-hand side of 3 drain current. We can also zoom in the turn-on junction of both cases. You can see the current is significantly decreased from original 9.7 amperes down to 2.2 amperes. And also, as I said, the current rising speed are almost remain the same. And also, after the turn-on junction, you can see current before entering the static region, the current is also much balanced compared to the original case without our proposed solutions. The only difference between the multiple devices case and the 2 devices case is that the number of your differential mode choke will equals to the number of your parallel devices. So when you only have 2 parallel devices, you only need 1 differential mode choke, but in our multiple devices, you will need, depends on how many devices you're paralleling, but it can be infinitely increase your number of devices. So you can parallel 3, 6, 9, and still using our proposed solutions, all of the drain current should be automatically balanced. So it leads us to the conclusion point. Sorry about all the words, but I want to highlight all of the summary in this slide is that first, for the dynamic current sharing, we've studied the feedback mechanism. We found there's a feedback mechanism, and it only depends on the power source mismatch. And also the layout of drain, gate, and Kelvin source can afford asymmetry, but the power source layout should all be symmetrical as possible to enhance dynamic current sharing, or you can also decrease your Kelvin source parasitic inductance, or increase the summation of your source parasitic inductance. And while these 2 methods help enhance your dynamic current sharing, in either matching the drain inductance or increase the summation of drain inductance doesn't help dynamic current sharing. And eventually, we propose the methods to balance the dynamic current. Even if you want to design a very unbalanced layout, it's fine. Just use our proposed methods, and you can always automatically balance the current. And it can work for parallel 2 devices and multiple devices. So this is my presentation for today. Thank you.
It's a very hot area. We actually see quite a lot of work trying to address the same challenges. I'd like to have some Q&A sessions. Any questions from audience?
Hi, Che-Wei. Thank you very much for the presentation. This is Slavko from ABB. Is the method that you proposed applicable for both TO247 with the 3-lead and 4-lead devices?
Unfortunately, I haven't started analyzing the 3-pin devices, but I think the mechanism should be very similar, is that they all depends on, during the switching junction, they all depends on what is the charging gate current, the degree of the charging gate current. So in that case, if our solutions can always balance this gate current, then it should be able to apply to the 3-pin devices.
Yeah. Okay, thank you. And how about power modules?
So for the power module, it's a little bit more tricky because in the power modules, the die is in parallel inside the modules, right? And also, before it reaching out to the external terminals, they already combined all together inside the power module. So it will be a little bit tricky when you put inside. But in our case, we only want to deliver this kind of idea, how you're going to balance all the current and what is the mechanism behind the dynamic current sharing. So eventually, it will come up to you to further optimize the differential mode choke that can put into the power modules or put into your own circuit. So we didn't focusing on optimizing the differential mode choke. We only want to deliver this kind of idea to all of you guys. Yeah.
Thank you very much.
Thank you.
Yeah, Hiro Akage from Tokyo Technology. I shared some related information. One of engineers from Fuji Electric, Japan, he presented more than 10 years ago very similar idea using differential mode inductor to not parallel connection, series connection of switching devices.
Yes.
Do you know?
I believe it is coming from one of the application nodes, and I think they're using the common mode choke for the series devices. So the devices in series, they try to use the common mode choke to balance all of the gate signal of each devices to ensure they have a balanced voltage sharing between each devices. But in our case, the idea is different. Is a little bit different. Is that first we found the mechanism caused by the unbalanced gate current. So we put a differential mode choke to balance the gate current. So this differential mode choke, the purpose is only to balance the unbalanced gate current, or you can also think another method to balance the gate current. But our solution is more simple, but it will be a little bit different from what Fuji they're working on.
Yeah.
Yes.
I know the engineer very well.
Yes.
So I just give it information.
Thank you.
Hi, thank you for your wonderful presentation. And I have a question that if there is any influence on the switching characteristics, for example, the switching loss or switching speed, if you add a choke on the gate drive loop, is there any influence on the switching characteristics?
So, first, good question. After adding the differential mode choke, right? The only thing that ideally, it should then have any leakage inductances if we only derive the mathematical model. But it always, in the real application, you always have some leakage inductance on differential mode choke, right? It may impact your switching performance, right? For example, the ring. But in our case, for the parallel devices, so two MOSFETs, they are both driven by the separated gate resistor. So it kind of like maybe like suppress a little bit impact coming from that. And also another thing is, although we didn't focusing on optimize the choke, we only twist the lead wire to round differential mode choke, try to minimize this parasitic leakage inductance. But in both simulation result and also the experimental result, we did not find any like a voltage ring or any switching behaviors like strange phenomenon in the waveforms. And also for the switching losses, I think it will be more balanced because the drain source voltage always decrease at the same time, right? And then the switching losses, when you have the unbalanced current, it always result in the different switching losses. But in our case, you can see the switching losses are very, very much balanced, and also the switching speed, the current rising speed, are almost the same compared to the original cases.
Okay, thank you.
Just a comment, you assume that the devices are identical.
Yes.
But what if there is a substantial difference in threshold voltage or transconductance? How could much this help or
So
affect?
good question. So that's actually I want to show one more like backup slide is that we do the device characterization of 4 different discrete device candidates. So based on these 4 very specific devices, they may come from a different time period, but I do the characterization result of a batch of the devices, both from the DigiKey or the Mouser. We see that in some cases, for example, the Infinite devices has a very, very consistent transfer characteristic. So our solution, I assume that the devices are identical. But when your device has mismatch, our solutions has no benefit in that case because I force the charging speed to be the same. But when your device has like a different transfer characteristic, one threshold voltage lower than another one, then it's still the one lower threshold voltage will still open faster. So our solutions has no benefit in that case. But I believe this issue can be alleviated in the future when the manufacturer devices technology can be improved. So in that case, we propose a solution is that based on this scenario, is there any solutions to still balance the drain current? This is our starting point. Yeah.
Oh. Maybe I have this completely backward, but you're putting an inductor in series with the source. Did you look at the effect on the turnoff stress, voltage stress on the drain, by doing that?
Stress?
Yes. So you put an inductor in series with the source, and I apologize if I got things completely turned around. It's been years myself since I've done electrical design, but you're putting a current through it, right? Okay. When you turn off, the inductor is going to reset itself, if you will. Okay.
Oh, okay, I see. So
yes.
In our case, we put a differential motor in the gate driving path, right? So I didn't work on that to optimize this show, so I didn't study the impact what you're talking about.
Oh, no, I meant when you showed adding inductance into the source to force the imbalance, but I also interpreted it as saying that you could force balance by adding inductance into the source, which kind of makes sense, but it would seem that it adds an additional potential for additional stress on the transistor. So is what you're saying is that no, this was just focused on the gate drive and this was just a means to an end, or were you saying this is a 1-2, but the focus was mostly on the a 1-2 approach to forcing balanced current, but your main approach was focused on the switching?
Yes, so that may be like several approaches to help balance the gate current, but our approach is like just putting this one to propose this kind of ideas.
Okay,
yeah.
so you didn't look at potential for increased stress?
No,
okay.
We didn't look at it. Yeah,
okay.
Thank you
All right.
for the suggestion.
Thanks.
All right, I think that's, thank you for Joey for
Thank you.